The camera is rolling. So, we in chapter 6 are learning about random variables. So a random variable is called that because it's a result from a statistical experiment that has numerical possibilities as results, and therefore we can define those possible results as a variable. And so we learned about random variables, we learned about transforming them, we learned about combining them. We actually did an example the other day where we had a normal distribution with random variables, but then there's this other thing called the binomial distribution. And that was where I had you watch the videos. And so I'm going to pick up right where the videos left off. Okay, so the videos left off with lessons on how to use your calculator. So again, I'm telling you, if you didn't watch the videos and all you do is copy someone's notes, you better watch the videos because you still don't know how to use your calculator, and you need to. All right, so I'm picking up at example 4. And it says, refer back to the example of rolling doubles. And that was the example that was in the videos. When you roll a pair of dice, the probability of rolling doubles is 6 out of 36, which reduces to 1 out of 6. So we have the probability of rolling doubles 1 out of 6, not rolling doubles 5 out of 6. X is being defined as the number of doubles we get if we roll the dice 4 times. And this was the probability distribution that was created in the videos. And at this point, I have said, let's sketch this probability distribution. And there's a reason I'm having us sketch it. It doesn't have to be beautiful. And we'll be referring back to this at some point. So if I were to do this, I would say X is going to stand for the number of doubles I get, my possible values, and this is discrete because I can either get no doubles when I roll, I could get 1 set of doubles, or 2, or 3, or maybe it's a really odd day and I get all 4 sets of doubles. Low probability of that happening, of course. So if I were to draw a bar for each one of those, I'll just say here's 25%, here's 50%. Just to make it easy on myself. So this one really is almost 48% chance of this happening. This is about a 39% chance of it happening. Only a 12% chance. Only a 2% chance. And again, your chances of rolling dice 4 times and getting doubles every time, don't plan on it. We're not going to say it's never, ever, ever going to happen, but it's maybe going to happen once in a really long time. Okay? And we learned a long time ago, and we could review this since we have an exam coming up soon. We have to know how to do this. We could describe that as what type of skew? That is a right skew. Okay? Now, I'll kind of jump ahead a little bit and I'll tell you, it's a right skew because A, it is a binomial situation. We already talked about that in the videos. But I also could have told you it's going to be a right skew because the probability was so off balance. Okay? Because 1 out of 6 compared to 5 out of 6. When it's off balance like that, you're going to end up with a skewed distribution. Had it been in the reverse situation, had it been 5/6 versus 1/6, can you guess what that distribution would look like? Okay, it's going to be skewed in the other direction. And if you end up in a binomial situation that there kind of is almost a 50-50 chance, can you guess what that would look like? It ends up looking like a normal distribution. Okay, so those probabilities, your probability of success versus failure, will give an indication of what shape your distribution is going to have. Now, when we were together on Monday, we reviewed how we would use our calculator to figure out what mu sub x is and what the variance for x would be or the standard deviation for x. I'm not going to go through it on the calculator. I'm going to tell you that if you went through all those steps that we learned how to do, you would find out that this mu is about 0.6667. I'm just going to 4 decimal places. The variance is 0.5556, and the standard deviation is the square root of that, which is 0.7454. Again, great opportunity right there. If you're still not comfortable how to use the calculator to do that, put that data in your calculator and practice using your columns and lists and see if you can get those numbers to come out. But here's the thing. For just any sort of random variable probability distribution, we would use our calculator in that, and use that method. But in a binomial situation, there actually are special formulas. Make your life a lot easier, but we need to derive the formulas, and then we have to review on how we're going to know if something is a binomial distribution, which would allow us to use the formulas. So to begin with, I'm going to start with a really basic binomial distribution. I'm going to call it variable B. This is going to be my random variable. And I'm going to say that two things can happen. I can either have success. I'm going to call that a probability of 1, or an outcome of 1. Failure is an outcome of 0. The probabilities, I'm not going to give quantities to. I'm going to give them variables. I'm just going to say the probability of success, I'll call it P for probability. And if the probability of success is P, the probability of non-success would be 1 minus P. Okay, just like up here, it was 1/6 versus 5/6. Right, so it's just 1 minus. And we are going to go through our table method using variables. And this is why they list Algebra 2 as a prerequisite for this class, because we do every once in a while get into some steps that require a little bit of algebra background. By the way, if you get warm in here, and feel free to crack open a window a little bit, because yesterday it got really, really stuffy. But all right, so if we were to begin our table, we say our possible outcomes are 1 and 0. And we have defined their probabilities to be P and 1 minus P. And basically what we're going to do is we're going through, where are my formulas? We are going through all of this stuff, but using variables instead of quantities. All right, so we know that we always have to take B minus the mean. Oh, we need the mean. We haven't calculated the mean yet. Well, let's see. Mu sub B. And to do the mean, this is where I said you don't have to use your calculator with the tables and the lists for the mean. You can always just take the value times its probability and then add it to the next value times its probability. But of course, that just comes out to be 1 times P, or P. Okay, so my mu is going to be P. My expected value is going to be P. Okay, so I need to do whatever's in the B column, 1 minus the mu that I just calculated to be P. So this is going to be 1 minus P. And then the next one's going to be 0 minus P, which of course is negative P. And then the rule is you have to square those things. Okay, so we have to do 1 minus P squared. Oh, we get to FOIL. We haven't FOILed in a while, have we? Okay, so what do we get if we multiply 1 minus P times itself? Algebra 1, people. 1 minus outside, inside would be negative P and another negative P, so negative 2P. And then P times P is P squared, and it's a double negative, so it is positive P squared. You got it. And then on this one, we have to take the negative p and square it, which just becomes p squared. The negative just goes away. But then the formula says you're supposed to take that and multiply by its probability. So I have to take this trinomial I just created and multiply by his probability, which was p. So basically, I just have to distribute p, and I'm going to get p minus 2p squared plus p cubed. And then I got to do the same thing on this one. I have to take that p squared, and I have to multiply by his probability, which was 1 minus p, and that's going to give me p squared minus p cubed. And then, if we were using our calculator, we get all that stuff done in the calculator, and that's when I exit my tables and lists, and I go into that one variable statistics, and I calculate to sum up that column. I need to add up everything I have here. So I need to take this trinomial, and I need to add it to this binomial. I need to add those together. Well, p cubed and negative p cubed are just going to cancel each other out when I add them. Negative 2p squared and positive 1p squared is going to give me a negative p squared. And this p doesn't even have a like term, so he's just, there it is. I added them together. There's your variance. And you're like, so what? What in the world does that mean? All right, what I'm going to do now is I'm going to factor off a p because it's the greatest common factor. That's why I said variance factored. So it's going to be 1 minus p. That's the formula for variance. And then the only thing you do to get to standard deviation is you take the square root of the whole thing. And you might look at that and say, what in the world does that mean? Well, it's the formula we're going to be using. That is the formula that we're going to be using, except for the fact we do have to consider how many times does something happen. We have to consider, in this case, for example, this one, our n was 4. We have to consider our n size. So that's why I said here, now let x equal, suppose whatever it was b represented, it happened over and over and over again. Like the apples, if you watch my videos. The apples I think were the notes we did on Monday that we said we were filling bags with apples. We just kept taking apple after apple after apple. So that's what's happening here. Whatever b stands for, we have it the first time, the second time, the third time, all the way down to, we call it the n time. If we have this, thinking about that apple example, mu sub x would have to be mu for the first b, added to mu for the second b, all the way up to mu for however many b's there are. So all I know is there are n of them, but they all would have the same answer. In this case, our answer was p. So this is going to be n times p. Because there were 12 of them, so I can just add them. There were 12 of them with the apples, and we said we could just add them together, or we just multiply by 12. Well, in this case, I don't know how many there are. So we just take this p, and we multiply by n, depending on how many there are. But over here, it gets a little messier. Because over here, remember the rule is you can't add standard deviation. You have to add variance. So you would have to say, I'm going to take the first variance, add it to the second variance, all the way up to, I'm going to add it to the nth variance. I don't know how many there are, but I know every single one has a variance of p times 1 minus p. So there's going to be a p times a 1 minus p, added to another p times 1 minus p, all the way up to another p times 1 minus p. How many p times 1 minus p's am I going to have? N. So we're going to do n times p times 1 minus p. But since we really want standard deviation, we would now have to now, are you ever going to have to know how those formulas were derived? The answer is no. And then you might say, then why did you show us? Why did you waste our time? I simply am not comfortable just setting this on the screen and saying, there's your formula, plug a number in, trust me. There's a formula, plug a number in, trust me. You might not even totally understand the derivation. I get that. I was in your shoes once, okay? I was a great example of a person, just show me the formula, show me what number to plug in, I'll get my answer. As a teacher, I can't do that, okay? I want you to know that these formulas didn't just come out of thin air. Okay? They literally came just from algebraic work, okay? You need to understand that these formulas only work if you know you have a binomial distribution. Okay, in the video, I talked about the bins, the B-I-N-S. If you do not know that it's binomial, you should not be touching these formulas. You go back and do just the generic ones. Okay, but if you know it's binomial, let me show you how much easier it is to use these formulas. Now, can you picture the steps that are involved to put this in your calculator to figure out the mu and the sigma? Okay, you guys, if you have been practicing, you're probably getting really fast. But watch this. Since this is binomial, let's say I haven't figured that out yet. I come down here and say, okay, for example 4, I'm rolling the dice 4 times. I know that the probability of success is 1 out of 6. 4 times 1/6 is 4/6, which reduces to, which as a decimal is, done. And then you're like, okay, so 4 times 1/6. So I roll the dice 4 times. Probability of success is 1 out of 6. Probability of failure is 5 out of 6. And if I type that in my calculator, I'll do the square root of 4 times 1/6 times 5/6. Here's your standard deviation, without having to go through the lists and the tables. But I'm going to say it again, these formulas only work in a binomial setting. You have to know that you're in a binomial setting. If you do not know that, then go back and do it the other way, okay? All right, the formulas, as I already showed you, they are on the formula page. So you don't have to memorize the formulas, but you have to know when to apply them. So here's an example. Back in the 70s, there was a thing called the Pepsi Challenge. You ever hear of it? The Pepsi Challenge, it was a whole commercial that they were trying to figure out what soda did people like better, Coke or Pepsi? And the commercials were literally, they would supposedly find random people in the mall or something and have them sit down and blindly take a sip of 2 colas, and all these people loved Pepsi better than Coke. Okay, and then you have, and what this example is kind of related to that is, You know, you have the diet sodas that the manufacturers always say, oh, it tastes just like regular. No, it never did. Coke Zero is close. It's what the closest. But okay, when they say diet taste, you can't tell the difference. Yeah, I can. Yeah, I can. Diet soda sucks. Okay? So, the makers of a Diet Cola claim that its taste is indistinguishable from the regular version of the same cola. To investigate, an AP Stat student prepared small samples of each type of soda in identical cups. Now think about the experimentation part of this from chapter 4. How they'd have to make sure they have identical cups. All the soda has to be the same temperature because otherwise the temperature might affect the flavor. Okay, same amount in every cup. Make sure no one else like drank or ate something first so their taste buds are, you know, think of how they would have to set this experiment up. Okay. She then had 30 volunteers taste each cola in a random order. Oh, we taste them in a random order. Yep. So some people taste the diet first, some people taste the regular first, and vice versa. They try to identify which is regular. If we truly assume that you can't tell the difference, okay, if we really assume they taste identical, and people like sip, and they're just like, yeah, regular. And somebody else like, oh, right. You know, if they really can't tell the difference, wouldn't you assume that half the people are going to guess A and half the people are going to guess B? If they really can't tell the difference, okay? X is going to be the number of volunteers who correctly identify the cola. So first of all, and I mentioned this several times in the video, they're not they, I, the authors of the AP exam, whatever, they're not going to tell you, check your conditions for, you know, for a binomial situation. You are going to have to very quickly be able to go through this and say, B, binomial. Either they get it right or they get it wrong. Okay. Each person is independent of the next one. Okay. And we have 30 volunteers, so it's going to happen exactly 30 times. And success versus failure, we're assuming it's a 50-50 chance. Okay. So this satisfies the binomial situation. You have to just be able to go through that in your head really quickly, okay? So I'm not even going to take the time to write that because it just takes me too long. All right, now it's just find the mean and the standard deviation. Okay, here we go. Because we have established that it satisfied our bins, we can then say mu sub x. I don't have to go through and set up a whole probability distribution. I can use my new formula. N times P. There are 30 volunteers. The probability that they guess correctly is 50%. 15. And intuitively, okay, the mean ends up being very intuitive for people. Okay, yeah, if there's really no difference, I would expect half of them to guess right and half of them to guess wrong. 15. And I said here, interpret both values in context. And that's what I would say here. After many groups of 30 volunteers trying to guess which is the regular soda, which is the diet soda, after many groups have done this experiment, I would expect 15 of them to guess correctly in the long run. Right? My standard deviation, N times P. So you actually take that answer, N times P, but then you multiply that by 1 minus P, and you're going to take the square root of the whole thing. So you're going to have N is 30, P is 50%, and the complement is also 50%, success versus failure, but under a giant square root. And I have that comes out to be 2.739. Yep.
Is that time you say like if they can't show the difference, they want to
Well, sure. Picture it. Let's say Coke and Diet Coke both taste identical. We know they don't, but let's say they did. And someone, Khadijah, handed you 2 cups, and they said, take a sip of each. Tell me which is the regular, which is the diet. Aren't you just going to go, if you literally can't tell the difference, you're just going to go regular diet. Okay, you're just going to guess. And half the people will guess right and half will guess wrong, because if they taste identical, they can't tell. Okay, so we're expecting half of them to guess right and half of them to guess wrong, because it's 50-50 if they truly taste the same. That's the big thing, and we're going to talk about that by the end of this problem. That's if they truly taste the same. Okay, now standard deviation gets interpreted the same way it always has. Standard deviation is average distance from the mean. So, after many groups of 30 people have gone through and done this experiment, okay, the number of people who correctly identify the soda will vary from the mean of 15 by about 2.739. Okay, how you interpret those does not change. These are still random variables. Keep those phrases about being in the long run or in the context of the problem. After many groups of 30 volunteers have conducted this experiment, I expect this to happen. And for any group, whatever does happen will vary from the mean by about 2.7. Okay, so again, I'm not writing this down just because I'm saving some time here. Now, back to the thing with the Pepsi challenge. I don't know about you, but I could always tell the difference between Coke and Pepsi. Okay, I always could. Pepsi was much sweeter. Coke had a little bit of like a bitterness to it. I haven't had soda since March of 2008, I think. So I don't think I swore off of it over a decade ago. Not a lick. So, all right. So this experiment, and the other thing I'd like to point out, many of these examples that I give you, I got from the textbook, and the textbook is authored by a real AP Stat teacher. And so many of the examples they used were literally things they did in their classroom. So this very likely was an experiment that an AP Stat student really truly did, okay? Of the 30 volunteers, 23 of them made the correct identification. Does this give convincing evidence that the volunteers truly can taste the difference? Okay, now, what's your gut? Yeah, we're expecting 15 just based on guessing, and we got 23 of them nailed it. Okay, so if you think 23 is way higher than the expectation, you know what else is way higher? What if 24 people had done it, or 25, or what if all 30? So what we do then is we calculate what is the probability, not just that exactly 23 of them guess correctly. We even give a little bit of benefit of the doubt here and say, okay, we'll allow this probability to get bigger, because we're going to do the probability that 23 or more. Okay, because if 23 is weird, 24 is weirder. So here's where the binomial calculation comes in from the videos. You actually have to calculate the probability of exactly 23 added to exactly 24. And in the videos, I said you're allowed to do the setup and show the first two. And then you may dot, dot, dot. And then what's the very last one? Can't go more than 30 because we only had 30 volunteers. The setups do not show what you type. Don't tell someone you're typing in a binomial PDF or a binomial CDF. No one cares. You want to show the real setup. And the real setup is, and as I showed you in the videos, I do all these. I start by setting up all my notations. I call them all parentheses, even though technically these first ones, I don't know if I call them parentheses, but so in those, we say we had an n size of 30, and we're looking at 23. We had an n size of 30, we're looking at 24. All the way up to an n size of 30, and we're looking at all 30 of them get it right. And in the first set of parentheses on each one, you put the probability of success. Now, from the beginning, we said we're assuming everything tastes the same, so success versus failure is 50-50. So we're assuming 50-50. But then the exponents represent, in this case, we're saying 23 of them got it right. So that's the first one. 23 of them got it right, which means 7 got it wrong. 24 got it right, 6 got it wrong. All 30 got it right, and nobody got it wrong. That's called a proper setup. There should be plus signs here too. That's called a proper setup. Now how you type it in your calculator, that's flipping up to you. Okay? You could do this by doing the binomial PDF for every one of these and adding them all together. You learned how to do this in Algebra 2 with me last year or the year before. And that's actually what we did. We typed in each one of these separately and then we added them together. But I didn't bother teaching you back then about the binomial PDF on your calculator. So I'm going to go to my calculator. I'm on my Inspire, obviously. And I'm going to go Menu, Probability, Distributions. There's a binomial PDF somewhere. It was option E, as I recall. N size is 30. Probability of success was 50%. Inspires, you have lower bound, upper bound. So you can literally say my lower bound is 23. My upper bound is 30. The probability is 0.0026. Now, think about that. That's the probability that 23 people got it right, or 24, or 25, or 26, 27, 28. That's 7 probabilities added up, and it's still added up to less than 1%. So if it truly is a 50-50 chance guessing, there's only a less than 1% chance that 23 or more people could get it right. Do you think that's a really big or a really small probability? Really small. Okay, so small that I doubt that's ever going to happen. In which case, you have to draw a conclusion, but it did happen. And the conclusion is, I think the original parameters were wrong. You know what I think was wrong? It's not 50-50. Okay, it's not. Now, again, you guys know that. You know that diet and regular don't taste the same. Okay? This is a statistical way to prove it. They don't taste the same because the chances of people guessing correctly are really slim. Okay? 84s, you can't go both directions. Okay, this goes from 23 up to 30. 84s will start at a number and always go down to 0. You've got to be really careful though. You're going to be tempted to type in a 23. You can't. You want 23 on up. So you're going to do the complement, which is 22 on down. So you're going to do the probability that X is less than or equal to 22 and do a 1 minus that. Distribution. Binomial CDF. 30 trials. P was 0.5. My X value, 22. 1 minus that, 0.0026. Most common error on 84s is people they'll take that 23 and they'll remember they have to go to the left, but they'll just use the 23 and then go to the left. You can't, okay? Think about if you made the probability distribution be 0, 1, 2, 3, 4, 5, 6, it's discrete. So 23 goes with them. It can't also go with them. All right. All of this, way back, all the way back before we started talking about binomial. way back here. They kept referring to all of this as based on independence. Independent. We're assuming that everything is independent. Okay? However many clients this guy gets is independent of how many this guy gets. Whether this person guesses the code correctly is independent of the next person. It's all based on independence. But sometimes independence doesn't matter. Okay? A cereal company puts one of 5 different NASCAR driving trading cards into a box of cereal for an advertising campaign. Okay, so we have 5 NASCAR drivers. They don't drive anymore, but whatever. Suppose the company printed 20,000 of each card, meaning there's 100,000 cards out there. Okay? One person buys 6 boxes of cereal at random. What is the probability that if they buy 6 boxes, they never get a Danica Patrick card? So let X stand for the number of Danica Patrick cards from 6. Okay, so you could quickly go through and do a binomial thing. You're like, okay, binomial. Either I get a Danica Patrick or I don't. Okay, every cereal box is independent of the next one. Okay, N, I'm buying 6 boxes of cereal. S, my probability of success is 20,000 out of 100,000 versus 80. Oh, wait a second. As soon as I buy a box of cereal, what happens? It changes. There's not 100,000 boxes anymore. There's only 99,999. We don't satisfy the F part of bins. So we're going to calculate the probability using old formulas. If X is the number of Danica Patrick cards, we want the probability that X is 0, that we don't get Danica Patrick. So if I draw the first card, now remember, my success for the way this is defined is not getting Danica Patrick. So on the first draw, I could be successful 80,000 times, because there's 80,000 cards that are not Danica Patrick. But how the rule for dependence worked is you have to assume you were successful. So we have to assume that we didn't get Danica Patrick the first time. Let's say we got Jimmy Johnson. Cool. So now the next time we draw, we have 1 less card. And we also now have 1 less here, because we have to assume that I now took a Jimmy Johnson card out of the picture. And then I'm getting 6 boxes. Oh crap, I gotta write this out 6 times. So this goes down to an 8. This goes down to an 8. And now they're gonna go down to 7s. I'm out of room. Okay, then they're going to go down to 6s, and then they're going to go down to 5s. I can do this. 3, 4, 1, 2, 3, 4. There, got them all in. That was the old rule for probability for dependent events. We draw 1 card, and then another, and then another, and then another. We're buying a box of cereal, and then we multiply these all together. Now, I won't sit and type those all in my calculator. I've done it before. If you take all of these fractions and you multiply these all together, you get about 0.262134 ... That is a legit answer. If this setup is true and you buy 6 boxes, that is the probability. You have a 26% chance that you're not going to get Danica Patrick, so you don't get a full set. Now, you might not be close to a full set anyways. For all we know, we got 6 Jimmy Johnsons. Okay, we don't. All we know is we have no Danica Patrick. We don't know who we got here. Okay, so I already told you we failed the condition for binomial. We failed the letter F. But what the heck? Let's just try it. Let's try using the binomial formula. Let's see what happens. What if we set this up and said there are 6 cards and I want to calculate getting no Danica Patricks? All right, remember, this is the probability of success. Success is I don't get Danica Patrick. Hang on. I got to think about this. Do I have this written down backwards? I don't know. All right. Well, it's all right. We want the probability of not getting Danica Patrick. What is that probability? Oh, no. I said that backwards. Because we are counting Danica Patricks. Okay, the fact is we are counting Danica Patricks. So Danica is considered success right now. Because we are counting Danica Patrick cards. So that is success. We're just saying we're not going to be very successful. Okay, so there is a 20% chance that we could get Danica Patrick, but we're calculating the probability that it doesn't happen. And instead, this happens 6 times, which, if you think about it, kind of looks like that. Okay, these numbers are a little bit smaller, but they're kind of like 80,000 over 100,000. They're close. So it's kind of like 80 over 100,000 6 times. Not quite, but close. So that's a binomial PDF. So I could pull up my calculator. Binomial PDF. There it is, option A. We're getting 6 boxes of cereal. We're counting, trying to get Danica Patricks, but we're talking about getting no Danica Patricks. .262144. So are the answers identical? No. But they are exactly the same up to the 4th decimal, which is pretty darn close. Technically, when you deal with these formulas, whether it's the generic formulas for all random variables, or whether it's the binomial ones, technically they're supposed to be independent. However, if your n size of your sample is that large, it might not matter. Okay? There's a condition for this. They literally call it the 10% condition. When taking a simple random sample from a population, you can use the binomial distribution as long as your sample, that's n, is less than 1/10 of your population. Or reverse that, your population has to be greater than 1/10, or some people prefer to write it like this. They're going to say, if I take 10 times my n, that has to be smaller than my population. That's actually the one that I use. So our n size in this problem was 6, because we were buying 6 boxes of cereal. 10 times 6, 60. Is 60 smaller than the entire population of all my cereal boxes? Yeah, there were 100,000 of them. The point is, even though we weren't replacing, we didn't take the box, open it up, dig through and get the card and then put the box back on the shelf. Don't do that. They don't like it. They're not going to like you at Walmart or Meijer if you do that. Okay? So you buy the box, you take it home, and then you go back and buy another box. even though you just changed your population size, you changed it so insignificantly that it doesn't matter, okay? So they literally call this the 10% condition. Your sample should not be more than 10% of the population, okay? Otherwise, you will violate independence. Now, the next page, I'm not going to spend a ton of time on because I actually already kind of broached it a little bit at the very beginning of the notes. In a binomial distribution, if you have probabilities that are about a 50-50 split, you will have approximately a normal distribution. This is good. It means you can use z-scores. But as we saw in the very first example, if your p is small, like the 1/6 for the dice, you're going to get a skewed distribution. Or if your p-value is large and his complement is tiny, you're going to get a skewed distribution. But when n is fairly large, the distribution will become rather symmetric regardless of the p-value. That's the part that also can save you, okay? So even if you have a really off-balance probability, but your n size is large enough, you still might be able to use the normal distribution. And they actually call this the normal approximation. And what this says is when you calculate your n times p, if that's greater than or equal to 10, and at the same time n times 1 minus p is also greater than or equal to 10, then you're probably safe enough. It means that even if your p or your 1 minus p, if they're off balance, your n size might be saving you a little bit. So there are two conditions. There's the 10% condition, which checks for independence, and there's the normal condition that checks to see whether you can use z-scores. You need to know this and this, and you need to know which is used for which. If you apply this and tell me that you're checking for independence and you use this formula, you get marked down. If you do this and you tell me you're checking the normal condition, you get marked down. This checks for independence. This checks for approximate normality. You need to know that. It is going to become important from now until the end of this class. Okay? All right. I'll make it through as much of this as I can. I'll save some time on part A, where it says explain how this satisfies the bins. All right, in a survey of 506 teenagers aged 14 to 18, the subjects were asked a variety of questions about personal finance. One question asked if they had a debit card. Do you guys have debit cards yet? Yeah, I actually got one for my sons pretty early on too. Just they weren't allowed to use it all the time, but there's an emergency. It was nice to have it. Suppose that exactly 10% of teens actually really have debit cards. I think it's higher than that now, but when this was written, it probably was. So X is a random variable that's going to stand for the number of teens in a random sample of 506 teenagers who have debit cards. Okay, so how does it meet bin? B, binary. Well, either they have a debit card or they don't. Okay, independent. I assume every kid is independent of another. Okay, now there might be a little bit of issue on independence. Will it maybe depend on your family and how your parents feel? Okay, so maybe it's not completely independent. All right, we'll come back to that, okay? All right, N, 506 people, got it. That's our random sample size. And P, the probability of having the card is 10%, and the probability of not having the card then must be, okay. So We definitely satisfy the B, the N, the S. The I is a little questionable, but we'll talk about that. So let's say it wasn't independent. This is where the test for independence comes in. Okay, the test for independence is the 10% rule. So you take your 10, I don't know, the 10 is just kind of an established protocol, okay? And then you multiply by your N size, and that comes out to be 5,060. And you compare that to your capital N, your population. Okay? Do they care about the equal, or they put in equal? It really doesn't matter that much. Okay. Capital N is your population. Who is our population here? Teenagers. Okay. Teenagers. It doesn't even say teenagers in the U.S. It just says teenagers aged 14 to 18. Do you think we can safely assume that 5,000 is smaller than all the teenagers in the whole wide world? Yes. Safely assume that there are more than 5,060 teens worldwide. So even if you think the independence rule was violated when you check your bins, you just got past it because you satisfy the 10% condition, just like the Danica Patrick thing, okay? Every time you pick a teenager, you might be changing the probability, but it doesn't matter. Got this, okay? Show the calculations for checking the normal approximation, because here's the thing. If it's a 10%, 90% split, you're off balance. You've got a small p, and a large 1 minus p. So right now your distribution would be right skewed. Okay, that's no good. So what we're going to do is we're going to show that even though our 10 and 90 are off balance, we're going to be okay. We're going to figure out what is n times p. Well, our n is 506, that's our sample size. And our p is 10%, which is 50.6. And then you're going to do n times 1 minus p. So 506 times 0.90, which is 455.4. And it's no coincidence that those add up to 506. Because this would be the expected number of people I expect to have credit cards or debit cards, and these are the ones that I expect don't. Are these both greater than or equal to 10? Yes. Can assume the distribution is approximately normal. I will expect to see all of that on your Chapter 6 test. Don't just say, check, I did it, check. What are you checking for? I'm checking to see if they're bigger than 10. And because they are bigger than 10, it means I can assume that the distribution is approximately normal. I want it just like this. All right, and then this would just be an example where we would say the probability that x is less than or equal to 40, and you would convert that now into a z-score, and you would do your normal CDF work. And that's the whole goal of trying to establish normality, because it allows us to use z-scores. All right, so I know I kind of rushed that at the end. Do the best you can, because I don't see you again until, yeah. So you've got some time to play some catch up. This stuff all goes with me. I take everything home every day now.
I know I'm putting.
Those love person.